Um, this is chapter 6, gases. One of the very attractive chapters. However, it's one of the trickiest chapters ever. The problem with it is the units. Units conversion between metric, English, metric, SI, metric. And thus you have to be really watching for this. Otherwise, it's a very, very attractive, very simple, the simplest ever. But I think the simplest ever is nuclear chemistry. Nuclear chemistry is very, very simple. There's no tricks in that chapter, nuclear chemistry. But here the gases is tricky because the fact this STS exam will give you different units of the pressure, different units of the volume, correct? So that's the problem there. Otherwise, the very attractive chapter, very easy chapter. It's not really difficult. So we'll start first with the kinetic molecular theory of gases. Well, if you look at this, kinetic molecular theory of gases. So one of the very basic knowledge of gases. Gases are always what? Moving in a straight line. That's, we have to know that. They what? Moving straight line. They don't go in crooked lines. They walk. I have air. Air made of mostly 70-something percent, 75% nitrogen, about 24% oxygen, and about less than 1% or close to 1% the rest. Moisture, carbon dioxide, group 8 here, helium, neon, argon. That's what? That's air. Now, each molecules of those different gases, they are moving linearly. So when they move linear. They don't make spiral movement or I don't know, crooked type of movement. No, just straight line. With this straight line, there is a problem. So they what? This is oxygen, this is nitrogen, they collide. When they collide, the collision will cause them, one will be giving, depending on what the speed, one will be giving energy, or the other one will take in energy, correct? So, and that's what's about the gases. The problem with the gases, they don't have a specific volume. They take the volume of the container. They don't have specific shape. They take the shape of the container. So if I will ask you now, what is the volume of air inside this room? Your answer will be, the volume of air inside this room is the volume of this room itself. Are you following me here? Because I cannot pinpoint a gas molecule. Oh, this is oxygen of the air. This is nitrogen of the air. This is the rest of the molecules inside the air. No, that's impossible because they are always in motion. They're always what? In motion. They don't rest. They're always in motion, and therefore it's very difficult to know the volume of the gas. So always assuming the gas and the shape of the shape and the volume of a gas is equal the shape and the volume of the container they are in. So, and again, when they move, as we said, they use what? They utilize their kinetic energy, half of the mass multiplied by velocity squared. We talked about it. So this is just a theoretical thing. We talked about this, and as I said, you can look at this theory here. So then we have, after we have done, we have to go look at the type of the pressure. It is gas pressure. So the gas pressure is, we have atmospheric pressure, correct? Everyone is following? So we have a manometer inside the lab, and how does the manometer? The manometer has, if you look, this is barometer, not manometer. The barometer is different from the manometer, correct? The barometer is working in the, give you the with the height of the mercury. You can look at the height of the mercury pressure, the pressure of the mercury inside equal the pressure is outside of the air. Okay, so now this is open here. Look at this. This is outside. This is exposed to the air. That's air coming in. When the air coming in will press this mercury is heavy, will go in here, will go up. Why we have chosen mercury? Why we did not have chosen or selected tabor or just H2O instead of mercury? Somebody will tell me why? Why is that? Why is mercury is good for measuring the air pressure? Somebody will tell me? Well, it turns out to be mercury is heavy in density. So if we have H2O instead of this one here, we will need H2O, the column here we have to be about 13.5 times. Are you following me here? So you get like a 3-story or 4-story height to get this column, and that's impossible because the mercury is 13.5 times, correct, dense than the H2O, and therefore it will take a lot of work on having this long column filled with the air. Mercury, just a small, tiny, not tiny, but it's doable. So what will happen is the air will pressurize or will push the mercury. The mercury will go up, and then we can say, okay, so the air pushing in stops here. That will be read as what? As the air pressure. Are you following me here? So the pressure from outside will come and pressurize the mercury. Mercury will go inside this capillary, inside this column, and when it goes inside the column, will settle down in a number. This number will be equal, like the air is pushing, and the amount of the pushing of air is then will stop in a number. That will be our air pressure. Will be read as air pressure. Now, here's the first thing of the trick of this chapter. You have the pressure is measured in all those here. So in metric, look at the metric here, and in the English, and in SI. Where in metric we have 1 atmospheric pressure. In English, the 1 atmospheric pressure is equal to 14.7 psi. Somebody will tell me what the psi stand for? PSI stand for what? PSI. Come on, guys, don't let me down. That's the pressure here. Pressure unit. Somebody? Pressure unit. Somebody will tell me? PSI. Here, guys. Pound per square inch. Inch square. Correct? That's the pressure. Pound, that's the unit in English, 14.7. How about the SI? The SI will tell me this is 101.3 kilopascal. Capital B to honor the scientist. See here? You have, for one pressure unit, you have 3 different what? 3 different units according whatever system you are using. And that's what this chapter is, the units in there. So now, you come here and say, well, in the metric itself, you have an issue there too, because 180 m in metric here is 760 capital T, tall. Whenever we have capital means you honor the scientist. Capital P here, you honor the scientist. Correct? And the second alphabet. So Tor is 760 Tor, or 760 millimeter mercury. So that's all in metric. So that's the pressure. Correct? That's the pressure. So, and let's look at the Can I have this one here? I'll stop here. Everybody has this? Everybody has this? Okay. We'll go and look at the volume, correct? And we'll go and look at the temperature. And that's what I said at the beginning. We have to be careful about the conversion of units. Otherwise, the chapter is straightforward. There's nothing really difficult. But the units you have to watch. And you have small, tiny worksheet or tiny sheet with you, putting all those units together so you can memorize them for the final exam. For this, our exams and quizzes, it's okay. You can open book, but in the final exam, there is no open book. So, can I take one out? Take it out. Everybody has it. That's the pressure. Let's take the pressure out. Let's do the volume. Well, the volume here, again, we have metric, then English, and then we have SI. Well, in metric here, because in the gases, you can see you have to have, this will take priority. This is very important. Always use metric because some laws are of gas laws. So we'll use liter. The unit is, the unit is liter, capital L, correct? And the SI, as I told you, is cheating most of the time, is taking the unit from the metric. We'll be using liter as well. Here we have big issue. The big issue in English system, because that's not, the English system does not, unique by itself, does not cheat or take from other system. The SI, most of the time, they cheat or take from the metric units, but English by itself. Tell me what's the volume you can think about in English. You know that. Come on, guys, don't let me down. What we can use for volume in English system? You heard about this, correct? You are. Looks like today it sounds like real Monday. So we have pints, we have quarts, correct, guys? We have gallons. We forgot about this. So we have fluids, fluid ounces, yes, fluid ounces. So that's unique, but you have to have what? A chart there to help you if you have something like this. I have not seen in the SS exam will give you very difficult. They use this general because at the end you have to use this one here, but you have to convert this one here to liters and convert this one here. This one already, liters already there. Bless you. Okay, guys. So, but you have all those here, unique English units to be transferred into liters. So, okay, guys, this is the volume. Let's take the temperature. Let's take the temperature. This is the difficult part of the of this chapter. Not difficult, but tricky because you have to know those. Now, if I have never seen this in, but if that's the case, nobody memorized those. Even myself, I don't memorize every units of all these systems here. So, but what will happen is they will give you inside the question, how much is this equal to, how many quarts equal to liter, correct? So, oh, that's a tricky one too here, guys. The centimeter cube, that's metric, but it's a tricky. Centimeter cube is 1 milliliter, correct? And 1 milliliter is 1/1000 of a liter. 1/1000 a liter. So you have to watch this. Sometimes they give you not a liter in metric, give you centimeter cube. Then you know 1 centimeter cube is 1 milliliter, and the 1 milliliter is one of the thousands of the liter, correct? 1/1000 of the liter. Are you following me here? So those type of this might come centimeter cube, because they wanna look at the work in the lab. We did 1 centimeter. Remember the first lab we did measuring the piece of wood. The piece of wood, we measured the dimension of it, and then the volume came out centimeter cube, and this is really is equal to 1 milliliter, which is, then you have to go to liter, you have to divide by 1000. So everybody has this? Everybody has this? Can I take it out? Okay, so let's take temperature. Let's take temperature. Okay, temperature here again, we'll do the same thing here. So we have metric. So we said the whole thing here is the volume. We use the liter. That's the desired one. Okay. So this is English, and this is SI. Well, here the desired is the opposite. Believe it or not, it's so tricky. It's K, capital K, and capital K is Kelvin. The name of the scientist, owner, so it has to be capital, Kelvin. Correct, guys? So Kelvin. So in the metric is centigrade Celsius. And this centigrade Celsius to have it converted to Kelvin. And in English, in what? Fahrenheit. This Fahrenheit has to be converted into Kelvin. Okay, guys? So that we'll have covered all these units, and let's go for the laws. Yeah, we are almost there. So, any question? Any question? And that's the most hard part of the whole chapter. So, can I take this one out? Take it out? Okay, guys. We'll say we have gas laws. We have about 8 or 9 gas laws. We'll look into them. First of all, Boyle's gas law, but I will say Boyle's law, because we said gas law here. So Boyle's will tell us the pressure of a gas is indirect proportional to its volume. So looking at this one here, so we can say Boyle's law is telling us that volume of the gas is indirect proportional to the, because indirect, this one here, this means indirect proportional to the pressure, indirect, 1 over. So 1 over pressure is indirect, correct? So out of this indirect, I can put this one here, cross multiply, get this one out to equal, then I have to cross multiply, so cross. I have PV equal constant. So meaning what? PV1 equal PV2 equal PV3 equal EETC equal what? Constant. So I cross multiply, then I have a relationship, and we will not go for this. We'll take those, we'll stop here because then we have this my initial state, and this is my final condition. That's initial condition. We'll stop on this. So that's Boyle's law. Okay, guys, I just do all the show you all the calculation. How does it look like? Now, with this in mind, this is Boyle's law here, guys. This is Boyle's law here. Boyle's law. So, right, BV1 equal BV2. Now, if I put this one here in a diagram, so it will look like not a graph. So this is volume. This is the pressure here. So the graph will be looking like this. Correct? Non-linear, not linear. So not linear. Not what? Not linear. Okay, guys, not linear. So this is the first gas law. Indirect proportional of the volume with the pressure. If you increase the pressure, and that makes sense. If you have a piston and the gas inside the piston, and you start pushing the piston down, what will happen? The space will be less and less, correct? So the volume takes of a gas, the container, correct? Volume. So the volume will be less. If you take the piston away, the volume will increase and the gas volume will increase as such. Correct? That's the one. Any question? Any question? Everybody has it? Everybody has it? Yes, no? Okay, let's the second one. So the second one here, we have Charles law, gas law, of course. So Charles law will tell you the volume of a gas is direct proportional to its temperature. So V is volume. So that's the key here, guys. P is pressure. T is what? Temperature. So here means direct. So like this, direct here, guys. Like this, 1 over temperature or pressure or volume, that's indirect. Okay, guys? So if you have it like this, that's direct. If you have it 1 over the temperature or pressure, 1 over those, that will be indirect. So that's direct. So I want to make it direct, so make it equal. So if I make it equal, then cross multiply. Again, you have to do what? Cross multiply. Okay, so this is 1, this is 1, correct? So it looks like V over T, 1, 1, equal V2, equal T2, equal V3 over T3, equal ETC, equal what? Constant. Okay, guys, we'll stop here. We'll say, well, this is our Charles law. This is what? This is our Charles law. This is initial condition. This is final condition. Okay, guys, that's direct proportional. So if I increase the temperature of a gas, its volume will go up. If I decrease the temperature of a gas, freeze that gas, its volume will be less. That's what it says, correct? Out of this relationship, I can put a graph. The volume is here, the temperature is here. So then it will be what? The graph will be looking, so it is what? Linear, correct? It is linear. So this is Charles' law. This is called what? Charles' law. Any questions so far? Any question? No? No question? Then let me take this one out. We'll have the question is Gay-Lussac. Gay-Lussac. Can I take this one out? Somebody's laughing. You have to be politically correct, but that's the name of the person. Gay-Lussac is a very good scientist, French. Gay-Lussac's law will tell us the volume, the pressure is direct proportional to the temperature. The pressure of the gas is direct. Now we know that's direct, correct? So cross multiply, this is over 1, this is over 1. Cross multiply, get this one to equal, correct? Cross multiply. I did not calculate how many laws until now. This is number 3, correct? Number 3, Boyle's, Charles, Gay-Lussac. Number 3. I did not number those, but you can number them, okay? So that will be P1, cross multiply, that will go down, correct? That will go here. So therefore, P1 over T1 equal P2 over T2 equal P3 over T3 equal constant. Okay, guys? Of course, when I mentioned that, I keep all the other conditions. The volume does not change. The number of moles does not change. We'll look into that later on. So we'll stop in here in the final. So maybe it is. And this one here is Gay-Lussac's law. Okay, the higher the pressure, the higher the temperature. The lower the pressure of the gas, the lower its temperature. So that's, and again we have initial and final condition. Okay, guys. So anyway, that's number 3. Number 4. Number 4. Oh, we can do the graph. The graph is if I have the pressure here, I have the temperature here. The graph will be looking at it's direct proportional, correct? So it has to be what? Linear. Correct? It's linear, correct? So that's again another one is Charles' law and Gay-Lussac's laws. Both of them they yield a linear relationship. So number 4. Can I take this one out? Everybody has it? Everybody has it? Okay, let's see. Everybody has this? Okay, let's take this one out. Number 4. Number 4 is, now we have boils, chars, lusaks. And number 4, we call this one here, I don't want to the gas, but I want to the combined gas law. Combined gas law. This one will be PV. I can show you later on how we come to this, but this one here is T2. I'll show you after that how we can come to this. This one here, the number of moles, amount of the gas is not changed. So amount of gas is constant. Means what? Number of moles does not change. Does not change. Correct? I'll show you later on, but that's what's happened. Again, we have the same type of setup. This is initial. This is final. This is just the conditions here. Number 5. If there has it, we'll go worksheets. We'll next Monday we'll do worksheets. Number 5, kinetics one out. If there has it. So let's take this one here. And then number 5 is ideal gas law. Ideal gas law will be given to us PV equal nRT. PV equal nRT. This one here is number of moles. R is gas constant. Gas constant. And it has a value 0.082 liter atmosphere per mole Kelvin. T is the temperature in Kelvin. In Kelvin. And V is volume in liters. And P is pressure in atmospheric pressure. Pressure in ATM. Atmospheric pressure. So this is what ideal gas equation. This is what ideal gas number what? Number 5. Number 6. We'll do those laws. I'll just show you here. Then I'll do it for you. Then worksheet will look at them. So number 6. Everybody has this. Everybody has this. Okay. Number 6. Number 6. Dalton's gas law. Well, Dalton's will tell us that the total outside pressure, so the total B total equal the sum of all partial pressure of gas in the container, partial pressure of all gases in a container. So I have here a container here, confined, and this container has CO2 and nitrogen and ammonia. So it turns out the P total will be the partial pressure of CO2 gas plus partial pressure of, correct? Partial means part of the total. Partial means part of a total. The word partial here, part of the total. The partial pressure of nitrogen plus partial pressure of ammonia. And if you have more, then you can add them up, plus whatever, if you have more here, plus whatever gases you have. Okay, guys, so the total pressure of gases confined in a container will be the sum of all their partial pressures inside this container. Okay, guys? Number 7. Can I take this one out? What's that? No, it does not have. This one has nothing to do with the linearity, no. The beginning of that had the linearity with the volume. Can I take this one out? Well, number 7. 5 or 6? 6 or 7? What's the number is? 7? Okay. So 7. Let's come up with the name gas laws at STP conditions. Guys, we have 2 minutes. That's good. S means standard. T means temperature. And P is pressure. So standard temperature is 0 degrees Celsius or 32 Fahrenheit or 200 what we said, 273, sorry, 273.15, 2.73 is 73.5 Kelvin. The pressure is just 1 atm. So we have gas laws, they use general condition, but we have specific, sometimes we can put this condition on those gas laws, then we have another law. So in this law here, guys, look at that. 1 mole of the gas, 1 mole of gas will give me always 22.4 liter of the gas. This is the law here. This is law. Gas law here. 1 mole of a gas will give me 22.4 liter of the gas. I'll stop here. One more. That's in the solution. Okay, has to do with concentration. That's called Henry's gas law. Henry's, but we'll come. That's next Monday, and that's it. Eight laws we have. Okay, guys, I'll stop recording here. We'll come back and look at Henry, although it's not per se gas. That's the solubility of the gas inside solution.